Gautam, Rajesh, and Shiraz for inviting me to this very special occasion of this Spenta test 2017. And it's really a great honor to have a chance to talk here. And so today I'd like to talk about this, some derivation of AdS metric, actually time slice of anti-De Sitter metric from the path integral description of conformal field theory. And here are collaborators, Pavel Kapta and Nilay Kundu, they are new postdoc in our institute, and Miyaji and Watanabe, they are graduate students. So my journey to this holography, this research of holography and AdS CFT, start from the simplest example and famous example of holography, namely 2D string theory, which is described by Liouville theory and coupled to matter CFT, and equivalent to C=1 matrix model already reviewed by very nice talk by Igor Klebanov yesterday. This is something my starting point of holography, and in this topic, one of the most mysterious aspects of this string theory, 2D string theory, is the existence of 2D black holes. And this is discovered by Mandal, Sengupta, and Walia, and also independently by Witten. This is a very stimulative result, a stimulative solution, and which is captured by this cigar-like solution in Euclidean signature, and this offers us the exactly solvable and a very simple model of string theory. And still, this solution poses a many mysterious nature of 2D gravity. And in this talk, I'd like to report a new look at this Liouville CFT in terms of more modern context of emergent spacetime in AdS CFT correspondence. And at the same time, I'm really grateful to this Indian community about hosting a lot of very stimulating workshops and conferences, and where I really enjoy this Yes, exactly. Also, I really enjoyed with Andy discussion when I was in Harvard, but I think it's still not clear how we understand this. I mean, world theory is solvable, but the interpretation of this 2D black hole from the viewpoint of holography is a really unsolved, very prominent problem. Totally agree. It's very, very mysterious problem for us. And also, really thanks to this leadership by Walia, always I enjoyed this conferences and workshops, which is really active and very friendly atmosphere, and which I learned so much. And also, that also caused me a real outcome. I will also mention later. But it's really appreciate this Indian community and Walia leadership. Okay, let me go on. So this here is my introduction. So I'm going to talk about AdS CFT, which all of you know very well. And one way to capture AdS CFT, or more generally, holography, is a geometrization of dynamics of quantum field theory. And one important fact behind this work is quantum entanglement. This is a recent development. And the reason why quantum entanglement plays an important role is that we can capture some sort of geometry from the quantum state in many-mode system or a conformal field theory or quantum field theory, more general. So this is a way to, originally it is quite algebraic structure. So this is a wave function of complicated many-mode system. It's like a lot of linear combinations, very complicated, but and algebraically complicated. But we can, if we look from the viewpoint of geometry viewpoint, then we can have some nice picture like anti-De Sitter space or some version of that. This is realized. One way to realize this is a so-called recent idea of this tensor network. So this is a way, graphical way to represent a complicated quantum many-body system wave function in terms of some kind of network of entanglement. I will explain a little bit later for this. And the reason why we have also this geometrical nature of quantum entanglement is come from also this holographic entanglement entropy, so which also I worked with Shinseryu, but also I want to emphasize that this final formula, this kind of complete version, which has a covariance, in the general covariance, and we assume some classical gravity limit, but it's a general formula which applies to any curved background with even time-dependent background. So this is a covariant and holographic entanglement entropy. So we have some anti-De Sitter space, and we have some minimal we have some surface, but we extremalize the surface area. Not exactly minimum, because in time-dependent case, we have to treat a low-Lentian space-time, but there are no minimum. It's like close to 0, so if it goes the right direction. But in a generic case, we can just look at extremalization of area, and if there are several candidates, we have to just choose minimum one. And this formula I found with Veronica Fleming and Mukund Rangamani, and this work exactly studied in India, especially the Indian Strings meeting 2006 at Puri. So really I appreciate this very interesting and very active atmosphere, which also leads to my really outcome for me. And so this is some surface, this is extremal surface, and so this extremal surface covers the region A. So entanglement entropy is defined by tracing out some part of the space, which we call B. And entanglement entropy for region A is computed by this area of the surface, which is, as I mentioned, it's an extremal surface which covers the boundary of A. So, but this entanglement entropy calculation suggests that this is a very heuristic picture, but we have some minimal surface, and the entanglement comes from some quantum bits. So quantum bits is penetrating this surface. It's much like black hole, but much more general in that you can choose any surface as a region A. You can move the position of A and also change the size and shape, anything you like. So that means this kind of entangling bits which penetrate this horizon. It's like 1 bit Planck unit area. It's usually also in black hole physics, but it's the generalization of that. But in this case, it's an advantage that these bits are everywhere in the space-time. So it might be natural to suspect that space-time in gravity is some collection of qubits of quantum entanglement. This is, of course, just a heuristic interpretation. And this, so from this, we speculate that space-time is like kind of network of quantum entanglement. This is also totally a heuristic picture, but there are some concrete framework which we can realize this idea. So this is a so-called tensor network. And tensor network is a graphical description of quantum wave function in quantum manifold system. In general, it's algebraically very complicated, but we write in terms of some graphical description. So this is something I want to review in the next transparency. But also I'd like to mention the next talk, we have some Matt Hedrick's talk, and who has a very interesting interpretation of this kind of network of quantum entanglement from the viewpoint of bit threads, which gives an independent approach, but might be closely related. So that's quite exciting future direction. So this, the best tensor network, one of the best tensor network which fit nicely with conformal field theory is so-called MERA network, multi-scale entanglement renormalization, and that's founded by Geoffrey Vidal, 2005. So this is a network, but this is actually, it looks complicated, but it's actually a very simple structure. So we start with many number of spins. We have spins. We want to construct, for example, ground state wave function here, but we coarse-grain the spins, 2 spins combined to 1. This is a kind of this triangle procedure, 3 vertex. This is called coarse-graining or mathematically isometry, which satisfies this norm-conserving property. And another one is just this box operation. This is a unitary transformation between these 2 spins. So this unitary transformation called this entangler, this cut it out entanglement. Originally, ground state is highly entangled in conformal field theory, but we cut entanglement and then coarse-grain into just a single spin without single spin don't have any entanglement at all. And the good point of this graphical description is that we can capture we can estimate the amount of entanglement entropy. So by tracing out this region, some region, so region B is here and region A is this interval, and we can talk about some entanglement entropy between A and the other part. But that essentially comes from this kind of links. There are no way to produce entanglement other than these links. So this number of links gives upper bound of possible entanglement entropy. And to optimize the result, it is good to minimize the number of links, which more precisely this intersecting links between this gamma A, which covers region A, and this MERA diagram. So we minimize it, and that it's easy to see. This is a log L. L is the length of this region A. This is let's take L spins in region A. Then each step we have one half spin, L over 2, and so on, so that this depth is a log L. So this log L is agree with scaling, which we know very well in 2D conformal field theory. So this scaling works very well. And at the same time, this space, it looks like hyperbolic space because it shrinks to zero size by some warping factor. And also, it looks like the holographic in the sense that this looks very similar. This estimation looks very similar to the analysis of minimal area or extremal area counting of entanglement. Though this is not exactly saturated. Motivated by this, also this is a kind of real scale, real space renormalization. And this looks like anti-Tadashi AdS3 correspondence. And this Brian Swingle, 2009, conjectures this, that tensor network of Mera, which is scale invariant, is correspond to some time slice of anti-Tadashi space. Real-time direction is not missing here because we are talking about quantum state, which parameterized by time. But we can see some space, part of anti-Tadashi space. So this is a very interesting and this is very stimulating conjecture, but there are several problems if we take this very seriously. So what about a special conformal invariance? And Mera itself looks like some, rather than Euclidean evolution, but it looks like some Lorentzian evolution. There are some causal structure. It might be related to Toshita space. And so this I already mentioned, but the entanglement entropy bound we can estimate, but to match, we have some, if we want to match with holographic result, we should saturate this entanglement entropy bound. So how can we do this? And the more serious question is, the more subtle question is how we can see the locality beyond AdS radius scale. So we want some locality up to Planck length scale, but that's completely missing in this Mera picture because it's everything is discretized. And each one vertex corresponds to roughly AdS radius scale. But there are many interesting improvements of this idea. So for example, the one which calls so-called happy model, Patarsky, Yoshida, Harlow, Prescue, they resolved basically these three issues in some kind of toy model, but they resolve this one ABC issue, which has a nice saturation of entanglement entropy, and some more improvement, which are also true for disconnected subsystems, which is given by Patrick Hayden and collaborators. And also there are other opposite ideas. Just stick to Mera. We don't want, just without changing the network. But instead of that, we just reinterpret Mera itself in terms of actually Toshita space, which is not exactly related to AdS space-time, but related to AdS space-time by some non-local transformation, which they call kinematical space approach. So there are many, many ideas recently. It's quite an exciting subject. But here, anyway, the one point that we have to treat some lattice regularization, some explicit lattice structure plays an important role. But in a quantum field theory, we want to make everything continue. So motivated by that, here I'd like to take a different route by describing the wave function in terms of path integral, just Euclidean path integral, rather than Lorentzian tensor network-like approach. So this is the main point of this talk. So let me start with the one basic principle, which we call its surface state correspondence. And this is actually just we just pick up the most universal part, universal idea of AdS tensor network duality. So if AdS space-time is described by some tensor network, then this kind of correspondence should be true. This is the idea of surface state correspondence. And this is very simple, just very simple statement. And it looks like almost empty, but this gives some formulation. So we take some sigma is some codimension to convex space-like surface. We take some, we have D plus 1 dimensional space-time, but we take space like D minus 1 dimensional surface. And then the argument is that for any choice of such a convex surface, we have some vector in a Hilbert space, in a universal space, like, for example, Hilbert space for conformal field theory. You have some quantum state. There are one-to-one correspondence between this. So this is actually true in tensor net in description. So more generally, like if we think about some quantum state dual to convex surface sigma, but in more generic situation like open surface or some surface which surrounds black hole, so topological obstruction, then in general we get mixed state. But if we don't have this kind of obstruction, then we get a pure state. But also we can discuss some zero size limit of sigma. If we shrink the sigma to 0, but still it's defined a state in a universal Hilbert space, but it gives some zero entanglement because there are no space at all. So such a state is in a conformal field theory case, we can have an explicit example of that. This is given by boundary state, like Cardi state or Ishibashi state. That has essentially no entanglement. And the reason why we claim this surface state correspondence just come from tensor network description. So this is a tensor network. Looks like a Miller network, but you can choose any other tensor network. But so this is a network, and at the boundary we have some, for example, ground state of conformal field theory or some ground state of contact field theory. But we can cut just in the middle. We can just think about some closed curve. Then on this surface, by contracting all indices, we can always define quantum state here. So this kind of surface state correspondence is obvious and trivial in this tensor network description, but just give some more continuing way to say this correspondence. So we are assuming this correspondence. Then the main claim in this talk is as follows. So we have this conventional picture of AdS and CFT correspondence. It's anti-Doshita space, this extra dimension, and AdS3 plus 1, and the boundary is CFT. So we are interested in, so let's start with UV quantum state. This ground state of wave function is realized at some particular time. This is a time independent case, we can just choose some particular time. So one way to realize this state is just pass integral from to minus infinity. This is a standard Hartree-Fock description of the flat space pass integral. So pass integral over infinite times, then everything projects down to ground state. But we can actually, what we want to argue is that we can optimize path integral. So if we imagine some discretization path integral, we can somehow coarse grain brackets and so on. So we can combine some, we can kill some unwanted information, and so that simplify path integral. Then we get this slice. This is a time slice in anti-Doshita space, which is namely hyperbolic space. This is optimized Euclidean path integral, and the surface state correspondence tells us that you can choose any codimension to surface. We can just choose just line here. It's looks like 3 dimensions, so just line. So if we choose any line, so we can associate one quantum state, and that's such a quantum state described by path integral of this region, not this region. This is a kind of Hartree-Fock state on hyperbolic space, not flat space. So this is a basic claim, and I'm going to explain this. So this, let's focus on AdS3 CFT2 because this gives a most clear example, and I would like to explain how to optimize path integral. So this is a conventional description of the UV wave function, ground state wave function in conformal field theory or any quantum field theory. So we have some boundary condition at z equals 0, particular time. Z is actually Euclidean time. Let's first regard z as a Euclidean time. Later, this is interpreted as a extra dimension in AdS space time. But this is a ground state wave function with path integral over here. And we can also define some path integral up to some particular Euclidean time z here. But still, we get the same wave function because this kind of time translation invariant state. So this is not interesting. But anyway, this is a starting point. But now what we'd like to do is some optimization. For that, we can notice that if we choose some particular time z, so then we have some path integral from plus infinity to z. So these are quite large. But you can see this explicit calculation, or just you can think about this exponentiation of path integral, that this cut it out the high momentum mode, which is greater than 1 over z. So this gives actually, this suggests that we can get rid of some information. We can neglect some detailed information in the region where large value of z. So when z is large, so essentially most of the mode is completely gone, because this is true because we are doing path integral for a long time. So we don't care about the information here, and gradually the information is increased. So this is explicit in an example of free massless scalar case. We have exact formula. So this phi k is fully transformed boundary condition. And we have some weight factor after integral of z, so it's 2kz. So we can get rid of some mode which have this property. So this is a sketch of this idea of optimization. So we start with square lattice regularization, but in the infrared, somehow starting point of this path integral, we can get rid of all details because here we have some unit long time path integral, so the all information gone, and gradually we can fine graining, and in the end, of course, we should reproduce correct UV wave function. So we have some microscopic regularization here. But in this picture, so now if we cut the path integral up to z, then we have a different wave function, So it's really wave function depend on z here, not here, but here it's depend on Z because of this regularization. And also because of this cutoff, it is quite natural to associate this space as a, you can claim this space-time as a discretization of hyperbolic space. I will come back more precise derivation of this space-time later, but already at this point, it's intuitively clear this space-time is described by, this space described by some hyperbolic space H2, which is a time slice of AdS3. And this is the main claim as already mentioned. So this is, we have some hyperbolic space here. We start from path integral from flat space, but modify by optimization so that we get path integral over hyperbolic space. And we can also, for example, match the conformal symmetry. So here, so original conformal symmetry in the flat space has this kind of generator. So this is a dilatation, translation, special conformal invariance. But this is, if we regard this Z is originally Euclidean time, but if we regard this Z as an extra dimension, this is the exact symmetry, exact geometrical symmetry, which realized on this surface HD. And we have some many other consistency, including HKLL state, some localized state, and so on. We can have a nice matching between this CFT and AdS spacetime about this symmetry. Same is true for global AdS3. So now, so far, I'm just give some heuristic approach, but I want to give some systematical analysis. And let's focus on 2D CFTs. So we want to characterize discretization path integral in terms of some quantitative, some quantity. And so we can pick up some, we can choose some metric. So the idea is we start with some curved metric and the rule sets a rule. One cell corresponds to one unit length. So this, if we specify the metric, that specifies the regularization, somehow lattice structure appears. If this metric is flat, then that just gives some square lattice. But if it is curved, it's possible to have some hyperbolic-like regularization. So anyway, we start with this path integral description, but now is a non-trivial function. Z is a metric. Z is non-trivial, but we path integral over this region. And with some cutoff epsilon, we always put some UV regularization epsilon. So then our proposal, which is the optimization of path integral, is here. So we just this simple-minded proposal. We just minimize wave function. Actually, the normalization wave function we want to minimize. So we want to minimize this wave function in terms of this widely scaling phi. Phi is a function of x and z. So all 2D metric always can be fit to this form. And we also put the boundary condition because we don't want to change the UV physics. We want to keep the same UV wave function. So exponential to phi, which is a metric component, should be 1 over epsilon square. So this is the same as original UV cutoff of the theory. Yes? In the CFT. We're not talking about any bulk. Here, just everything is CFT. Yeah, we do this. This phi is just a field in the CFT. Thank you very much. So, sorry, these are Euclidean time. Just Euclidean time in CFT.
Euclidean time in the CFT.
Yeah, here I'm not talking about any AdS CFT, just CFT calculation.
Yeah.
Yeah. In the end, we claim that it's interpreted as a radial direction anti-Tadashi space.
This Z is unrelated to the earlier Z.
Yeah, exactly. Related later, actually.
Okay.
So so far, everything is just conformal field calculation. Yeah. X is one, space direction, Z is Euclidean time. And we fix up a UV condition. And the thing is that we want to minimize this normalization. So the reason this normalization estimates a repetition of the same operation of path integration. We want to optimize. We want the most efficient algorithm to compute this quantity, this path integral. So if we try this, and this is very famous fact that if we do some widely scaling 2D conformal field theory, the factor appears. This factor is come from conformal anomaly. It's captured by Liouville theory. So this is just Liouville. By the Liouville field, and we have a UV cutoff which gives Liouville potential. And that means this proposal claims that we should minimize this Liouville action. Then there are nice minimum indeed, and that's exactly given by hyperbolic space. After optimization, we get hyperbolic space. And this gives in tensor network language, this should be the most efficient tensor network which create this ground state with function for conformal field theory, and just using this motivated by original idea of tensor network duality between this time slice of AdS and this tensor network diagram is this claims that this H2 is exactly the time slice of anti-Doshita space. So, and we can do the similar analysis for BTZ. So I don't have enough time, so I just cut it out. But in the end, if we do that, we just minimize the Liouville actions, then we get Einstein-Rosen bridge of BTZ, which is the correct time slice of the BTZ black hole. And we can talk about also excitation. So we can put some, now we switch to global AdS3 and we excite some one point. Then this excitation, the primary operator, is roughly captured by this, this scaling of this widely scaling. So then we have to minimize with Liouville action and also this source term because we add some excitation. And we get this delta functional source. And after this, we get some deficit angle geometry, which agree with what we expect in AdS CFT. Some just time slice of back-reactive geometry with some massive particle. This precisely agree when this H over C excitation is small, faster order. But the higher order, we have to so this disagree. But maybe if we use the result of quantum Liouville theory, this is actually modified. This classical Liouville theory here. But if we derive in terms, if we use quantum Liouville theory, it's precisely agree. So probably we need some quantum nature of this duality. So this summary. So we have some path integral and we excite it here. So but once we excite here, so we cannot coarse grain a lot. We have to actually find, we need some fine graining near the nearby excitation. And this is this kind of picture of this lattice structural mesh. It looks very similar to what we learn in general relativity. So if you have some particle here, massive particle, it bends the space-time, and indeed that happens also in path integral discretization if we want to optimize the result. And just mention other dimension, and just quickly finish. So this AdS2 CFT1, and at first sight we have trouble because here there are no, if we assume no conformal anomalies, so just 1D, so then we have only UV regularization term, which is Liouville potential, without the Liouville kinetic term. So then we cannot optimize, we cannot get a minimization. So it's have a trouble, but this owing to quite recent development, like this SYK model, we have lots of folks, David Gross, Hugo Perano, and Gautam Mandar, Spia Sachdev. It's a very beautiful model. And owing to this progress, somehow we get this Schwarz derivative term, which rewrites this in terms of just kinetic term of Liouville field. So now we have some nice minimization, and we have a stable solution, which this looks trivial, but this is very important because in 1D, it's all metric deformed into any form. But anyway, there are some stable solutions. This is quite important, and this also guarantees this minimization procedure. And similar thing, we can also do the same analysis on higher dimension, like especially AdS4, CFT3. So in that case, we can start with very simple action. There are no conformal anomaly, we just have UV divergence. So this Einstein-Hilbert term, this comes from Tito-Kernel approach. And by minimizing that, we get hyperbolic space. And also we can reproduce at least first order perturbation of localized excitation, which is exactly given by AdS black hole. Okay, so these are all of my talk. And just here I summarize the conclusions. So this optimization path integral state gives some gravity dual of this AdS CFT correspondence. This is our proposal. And this fit very nicely with this interpretation of tensor network in terms of time slice of anti-Doshita space. And also this path integral approach gives the same quantum state, actually below the UV cutoff. And so there are interesting future problems. And so we claim that optimization path integral gives some optimization also of tensor network. And this actually optimization procedure, it looks like very informational theoretical procedure, but it looks like equivalent to solving Einstein equation. At least we confirm this in the first perturbation. And more nonlinear part, maybe we need a little bit improve this statement, but at least first order perturbation, this is true. And this might suggest some very vague idea, but this AdS CFT might be some fastest supercomputer. Some similar aspect also appeared in fast scrambling and some this highest Lyapunov exponent and so on, but maybe similar thing to do here. And finally, so I'd like to come back to say that congratulations for happy birthday, Spencer. Thank you very much.
Are there further questions for Tadashi? The idea was that you work on in the CFT, you optimize, you have this wave function and you optimize its norm and you get a metric in 2D, let's say for CFT2. And then you interpret that as the metric in the bulk on a particular time slice?
Yes, exactly. Because we are specifying a particular state, fixed time, so it should associate some time slice.
Okay, I see.
And one way to understand this also in a standard context, maybe we can understand this as some conformal transformation. For example, we have some UV boundary here, but we can change this UV cutoff so that it's space dependent, we can go this way. And then we reach this minimal time slice. Yeah, think of that.
Okay, thank you.
Yes, go ahead, Andy.
So there's a very well-developed mathematical subject on which there are many interesting and surprising results about foliating Euclidean spaces with slices of constant extrinsic curvature and completeness and so on. And so your description of it in terms of the metric, that's in a particular coordinate system. And I'm wondering if there might be a more geometric description of what, if it could be related, if this could somehow be related to finding the slice of constant extrinsic curvature, which are also minimizing something.
Thank you very much for your comment. So far we only discussed the simple example, like static example. But if we want to generalize to time dependent case, definitely this kind of general aspect should be necessary and really.
Right. Are you hoping to make an exact correspondence between the both?
Yeah, in the end, we hope that it also can be applied to any general background with time dependent. And with appropriate choice of time slice, as one candidate, as you say, it's like some constant.
So what will you do about the fact that beyond classical or maybe first-order perturbation theory in quantum gravity, there is no well-defined geometry. It's fluctuating. I mean, is there hope to promote something like this to an exact statement about a relation between things, bulk quantities and boundary quantities?
Yeah, that's a very deep question. But maybe if we just take AdS CFT with classical gravity limit and with some small perturbation, so like some String effect and so on, some one over n, first order for 1 over n, maybe we can see, we can do a similar analysis. But I'm not sure about the full quantum. Really, just for example, 1 over n order 1, then, because we don't have enough way to analyze this function. But so far, this 2D example is quite universal. It can be applied to any conformal field theory because we just use Liouville theory. So that might give some hint to go that direction. But I think it's a very deep question, very, very interesting question. But still far from the answer.
Spenta?
Tadashi, I'm just trying to understand whether it is related to some things which people have thought about a long time ago, that if you take a theory of matter or conformal field theory coupled to 2D gravity, then you can talk about the gravitational dressing of operators, actually. Yes. And in some sense, in many cases, you can actually interpret the Liouville mode as a space or time dimension, actually. Yeah, it's very similar to that.
Very similar. I think it's like this gravitational, it's very similar to gravity.
Exactly.
But somehow power is opposite because of this prescription.
Sorry?
Power is actually opposite.
I understand, but
because of this.
The general idea is precisely that, right?
Yeah, exactly. Exactly, I would totally agree. So that we just put the prime operator, but not the scale imbalance, so we have to add this kind of scale. Exactly the same thing happens. It's like higher dimensional.
Can you do non-conformal field theories?
Yeah, that's a very interesting question. But here we use some Liouville action, which is only true for conformal field theory. For this more general, like massive theory, we expect something similar quantitatively because if we have some large mass gap, we can get rid of information here definitely. So that means we have some capped solution, which is we call AdS spherical and so on. So intuitively true, but just we don't have, currently I don't have somehow managed to analyze it. But numerically, I think will be possible. We can optimize path integral numerically and requiring UV wave function is still, we get the same. We can explore all backgrounds like mass gap and scalar field and so on. But the real calculation might be.
Suggest that we thank Tadashi